The inverse function theorem in several variables is one of the most used results from real analysis to branches like differential geometry. In this course, we are focusing on one variables. So let me just state and prove the theorem in the one variable case. First, let's begin with a somewhat simplistic statement, which we will in a moment generalize to the more general version. Theorem: let f from closed interval a b to r be a continuous function. Continuous function, of course, a is less than b. Assume that f is differentiable in open interval a b, and further that f prime of x is strictly greater than 0 for all x in ab. Okay, then f is invertible and its range is f of a, f of b, and the inverse function g from closed interval f of a, f of b to ab is an increasing differentiable function, strictly increasing, I might add, strictly increasing differentiable function with the derivative at a particular point y is equal to 1 by f prime of x, or rather 1 by f prime of g of y. Okay, so let me read out this statement. You have a continuous function from closed interval a b to r. We are assuming that f is differentiable in the open interval a b, and further that the derivative is greater than 0 at all points. Now we already know that under these hypotheses the function f will be strictly increasing. Therefore, we have already shown that f is invertible in an earlier module, and not only that we shown that f is invertible, we have shown that the inverse is a continuous function. So this inverse being a strictly increasing function is rather obvious. So we have this inverse g from f of a, f of b to ab. The key assertion is that this inverse is differentiable, and you have a formula for the derivative of the inverse. Now the statement is long, but the proof is easy. Proof. We already know. Please check the notes for precise references to the earlier results. We already know from earlier results that f is invertible and its inverse g is continuous. This much we already know. Well, what we do is the following. Let f of a be just alpha and f of b be beta. We have this function g from closed interval alpha beta to closed interval a b. Okay, the fact that this is strictly increasing is obvious. Okay, now we have to show that g is differentiable on, so let me be ultra precise, differentiable function on open f of a, f of b. Okay, now we have to show that g is differentiable. So what you do is fix alpha less than y naught less than beta. We have to show differentiability at this point. Okay, now because this function is going to, this function f is actually a bijective function. It's certainly injective and surjective. We know that we can find x naught in open AB such that f of x naught is equal to y naught. Okay, in fact this point is unique because the function f will be strictly increasing because the derivative is greater than 0 everywhere. Again, check precise references in the notes. Okay, so we have f of x naught equal to y naught. Let y in alpha AB be near y naught. Okay, again we can find x in AB with f of x is equal to y. Okay, now all this is a setup to take the Newton quotient g of y minus g of y naught by y minus y naught. And by the way things have been set up, this is nothing but x minus x naught by f of x minus f of x naught. We have set things up so that this happens. And this is nothing but 1 by f of x minus f of x naught divided by x minus x naught. Okay. Of course, this is valid if x is not equal to x naught. All this is valid if x is not equal to x naught. Okay. But g is continuous, which was how we began the proof. G is continuous. So if y approaches y naught, then this point x must approach x naught, simply because x is just g of y, and of course g of x naught, g of y naught is x naught. Okay, so limit y approaching y naught of what we are interested in, the Newton quotient g of y minus g of y naught by y minus y naught. This is same as limit y approaching y naught of 1 by f of x minus f of x naught by x minus x naught. From the remark I just made that as y goes to y naught, x goes to x naught, so this quantity inside just approaches 1 by f prime of x naught, which is just 1 by f prime of g of y naught as required. Okay, so the proof is fairly straightforward. You just compute the Newton coefficient. The only key part is that there is a function g that is inverse, that just follows from the fact that f is strictly increasing, which follows from the fact that the derivative is greater than 0. So this is typical of the proofs in mathematics. What we have done is, over the course, we have proved several results. Essentially we are just combining all of them, and this proof is immediate once you combine all of them. Okay, so immediate remark, similar result is true if f prime of x is strictly less than 0 for all x in AB. So that means f will be a strictly decreasing function. Then I had left an exercise for you earlier to show that in this case f is actually, the inverse of f actually exists, and the inverse of f is going to be continuous, so on and so forth. It's exactly the same proof we'll go through. Okay, now I'm going to state the general inverse function theorem. And I'm not going to prove it because it should be rather obvious from the theorem that we have already shown. This is the inverse function theorem. Let f from open interval AB to R be a C1 function. Recall, this means that the derivative of f exists and the derivative is in addition continuous. Suppose for some x naught in AB, some x naught in AB, f prime of x naught is not 0. F prime of x naught is not 0. Then we can find open sets U subset of AB such that x naught is in U, and V subset of R such that f of x naught is in V, satisfying number 1, f is bijective, or rather f restricted to U is bijective, and its image is V. Okay. 2. The inverse of f restricted to U is also a C1 function. Okay. Now I'm not going to prove this intentionally. The crux of this proof is already contained in the previous theorem. I want you to sit down and think about this and prove this theorem. It will give you a sense of satisfaction simply because this theorem in its several variable incarnation is one of the most used results in differential geometry. So this concludes this module. This is a course on real analysis, and you have just watched the module on the inverse function theorem.